goal of actually programming my first app, which I am not the most hands-on techie person. So I thought just listening in as you're doing this, I'm not engaged in it, but just it would start my vocabulary. So here's Trav.
Alrighty, 1 second. Sorry, trying to get this set up. Alright.
Okay, you good to go?
Yep.
All right, so for this week you looked at Angular SQL stuff, right?
Yeah.
Tell me what you learned about that. Give me the lowdown on Angular SQL.
I just I don't remember all of it because I did it a little bit ago, but how to grab the data from an SQL table. I don't remember all of it. I did it last Sunday, Saturday after class.
Okay.
Let me see if I remember any of the
I'm going to bring up the lecture stuff here. Now let's talk about SQL a bit.
Yeah.
Let's see, somewhere in here we have database stuff, I think. Okay, so let's talk about it here. All right, so we're going to actually work backwards a little bit. We're going to talk about SQL, then we're going to talk about kind of where it fits in the world, and then we're going to look at Angular events.
Yeah.
So just based on what you read, what would you tell me SQL is? Just SQL, not as it relates to Angular, just SQL in general.
It's a data I don't know what a database, a nice interface to call and set data from a database.
Okay, yeah, it's fair enough. So it stands for Structured Query Language, and it's really a language for querying the database, for asking the database for information. All right,
Yeah.
so we're going to call this a standard language for asking a database for info. All right, so that's what SQL is. And we started talking about design patterns. I don't remember if you were in on that or just saw it in the the lecture stuff here. But one of the things that has been an overarching theme as we've been going through this stuff is this idea of standards. Everything modern, all our modern software development stuff relies on there being standard ways of accessing things. So today, if you're talking to some API, grabbing weather data or grabbing whatever from the web, it's going to come in JSON format because that's a standard format, and we don't have to worry about learning how to digest information from 30 different sources. You learn how to digest information one way, i.e. JSON, and then you can just grab your information from different sources and just see what's being offered by those. Right? Well, the same thing is true with database stuff. So if we look at the history of database. Hold on, I'm getting a lot of feedback here. Hold on. All right, let's see if that does it better. Okay, so if we look at database in general, what's the goal of a database? Goal of a database is to be able to store information in a way that is queryable. Okay, queryable, I'm not sure if that's actually a real word, but we'll pretend like it is. Okay, so we want to store information in a way that is queryable. So if we go back a long time ago, kind of in the early days of software development, what do you suspect our early databases were? If you had a software project that needed to store some stuff in between runs of the application, where would you store that information?
I'm not sure. On a chart?
Yeah, see, it's kind of an interesting interesting question, because most people answer the exact way you answered. It's like we've forgotten about files. They've become so ubiquitous to computing that we don't actually use them anymore, or we don't think about them anymore. So in the early days, we would have just used the file. All right, so a file, just like a doc file, or for Microsoft Word or anything like that, just a single file that sits on your hard drive that has information in it in some format. All right, so we would use it. Go ahead.
I thought you meant like a physical, like a server type thing where you stored it. Yeah.
Sure. Yeah. No, I'm just thinking about we're going back to the very, very, very beginning. We want to think about how we got to today's databases. What was our first choice? So, if we think about ourselves as very, very beginning developers, and we don't know anything other than what basic computing skills. If we needed to store some stuff from our application so that we can load it up next time we run the application, reasonably speaking, we would probably put it in a file, because that's, most people who use computers at least know about files. They might not know about SQL or other databases or any of this other stuff, but they know about files. So that's a way of storing stuff longer term. All right. So obviously, if you have if you go and grab an iOS application or Android application or any other piece of software today, and it's storing stuff between sessions, a large percentage of the stuff that it's storing is not going to be in a file. It's going to be in something else, because files are very, very slow. Okay, files are very slow. Why do you suspect files are slow?
I have no idea.
Okay, so this kind of continues to go.
My mom says,
go ahead. What did you say?
My mom says indexing.
Okay. Well, that actually probably has something to do with it. So what you're really talking about is the operating system itself trying to keep track of all the files that are on the hard drive. And that takes time. And that's related here to the answer. So, whenever we talk about performance, we want to think about all the different little players that are involved. So a file is just one little piece of the puzzle. If we were to look at a picture here, let me just kind of drag this up. So here's our actual file right here. And where does this file live? The file lives on a hard drive. Okay, and who manages that hard drive? The hard drive is managed by the operating system. All right, so these are kind of the three players that are involved in a file even existing. All right, so this is one little bit of information that sits on this. If we think about this as like in a city, and this is the state that governs it. All right, so the real reason why files are slow has to do with the hard drive itself. All right, and that's starting to change in modern day computing. So historically, go ahead. Yep, solid state. So when we talk about hard drives, earlier hard drives were mechanical.
Yeah.
Okay,
but like SSD improves the performance.
It does, but only somewhat. It's not like a night and day difference. So if we talk about mechanical versus SSD, solid state drives, the
Yeah.
real difference is heat and probably how quickly they wear out. And because there's less heat, they can push them to higher speeds without worrying about mechanical breakdown. So that's why you get the increased speed. The real slowdown between either of these, the reason why we consider hard drives to be slow, really has to do with, in terms of their physical abilities being slow, has to do with can read / write one thing at a time. That's it. So if you have an application that is trying to bring in 50 pieces of information. Okay, let's say you're trying to bring 50 pieces of information into your application, reading it from a file. That's fine, but that's going to be 50 read writes for that file. And at that same time, while you're reading and writing from that file, you're competing for this resource, the hard drive, that the rest of your operating system is also trying to use to index stuff, to do file backups, that kind of stuff. So, this hard drive is a resource that is in demand. There's lots of things in the operating system that all want access to that hard drive, as well as your one program that is trying to get those 50 pieces of information that it has to get one thing at a time. All right, that makes some sense?
Yes.
All right, so mechanical hard drives, solid state drives, because they have the ability to only read and write things one at a time, they're slow because of that. Now, from a human perspective, they can read and write things very quickly, from our perspective. But from a computer program's perspective, where it's going to make those 50 requests in a fraction of a fraction of a fraction of a second, we're going to notice the slowdown. All right, so that's our slowdown there. Now, on top of that, we think about the entire process of what our computer program looks like. And let's go ahead and put it in the context of our Angular stuff that we've been working with. So we have our Angular software that is running on a web browser. So let's just assume it's Chrome for right now. So it's running on Chrome. Chrome is running on the operating system, which is one of the software applications that's running on the CPU. Okay, so Angular gets interpreted by Chrome, which is managed by the operating system, which is vying for CPU time. All right, so now this application, Chrome, it's the guy that's going to be waiting in line for the CPU. So we need to think about the nature of our CPUs here and say a CPU is a resource. So think of this like the line at McDonald's or something like that. During the lunch rush, 100 people are running into McDonald's and they all want to order lunch, but there's only 2 registers open, or there's only 1 register open. Well, one register is a CPU. So each of those people, each of those hungry customers are all vying for this one resource, so there has to be a line. Okay? Now, the human version of a line doesn't necessarily work the same way in a computer. We do have a thing like priority, so certain applications have a higher priority than other applications, so they might be able to cut the line a little bit. But at the end of the day, for this example, we could still think of it as kind of first come, first serve. Okay? So this CPU is processing our instructions for Chrome, which we fed it through our Angular software. All right, now what do those instructions actually look like? So when we think about our code that we've written, let me go ahead and get that opened here, because we're going to be getting back to that here in a few minutes.
Yeah.
I got Sublime's opening here. All right, so we think about all of our code right here, all right, that we've written, And all of this is going to turn into, we can take it to the extreme and say little zeros and ones, but realistically what it gets turned into is a low-level language. So earlier in the lecture set, we talked about high-level languages versus low-level languages. All right, and a low-level language is a language that has a one-to-one relationship with the CPU, which means that every instruction, every line of code in a low-level language is exactly one little magic trick the CPU knows how to do. So it's kind of like walking up to the register at McDonald's and ordering fries. Then the next magic trick is ordering a Big Mac.
Yeah.
So on and so forth. You're doing one thing at a time, and that's what a single core CPU can do at an individual point in time. I realize that our modern computers are all dual core or quad core, but for this example, it works best to think of it as a single core, because things get 10 times more complex when we start thinking about the multiple core type stuff. But in any case, so our CPU is going to be receiving one instruction at a time from Chrome for the time period that Chrome gets the CPU. Okay, so if you think about it like ordering lunch at McDonald's, you don't get to put your entire order in, potentially. When it's your turn in line, you get to, order as fast as you can for, some fraction of a second, and they kick you out of line. You got to go back to the back until you're done. Keep cycling back through the line. All right, so the CPU is going to be handling instructions from Chrome, which then, as those instructions get finished, it'll make your Angular code process or whatever and show up on the screen. Okay?
Yeah.
So there's a lot of moving parts here is kind of the point we want to get out of this. A lot of moving parts that all lead to the complexity of computing. All right, so when we think about our file, when we talk to the CPU, our program's talking to the CPU through either directly or through a web browser in our case. We're asking that CPU to go ahead and write something to the hard drive. Well, when we talk about CPU, there's two different kind of paths on the CPU. We have the number crunching path.
Yep.
Okay. And then we have the I/O path. Input output. All right. And the I/O path is very, very slow. All right, and because I/O is slow, we don't want to bog down our CPU with that I/O path being going. So we can actually see this, or we can take our McDonald's example further. When you go into a McDonald's or any fast food place today, most of them have their soda machines out where you can go and give yourself your own refill, right?
Yeah.
Okay, and why is that? It's because if you walked up to the counter and talked to the CPU, talked to the person at the register asking them for the refill, they have to delay helping the next person while they go and fill your soda. And filling the soda takes some time, however fast the liquid can fill the cup. All right, so it's considered to be inefficient. So rather than doing that, what they've done is they've offloaded the I/O. We're going to call filling the soda I/O. Okay, so they've offloaded the I/O to the customer. The customer can go up to the machine and serve themselves so they don't bog down the CPU with their ordering. Okay? So the CPU can work as efficiently as possible. So that means whenever we do I/O stuff, we have to leave the line in order to go do I/O stuff, because I/O stuff happens separately to that. So now think about the way a computer program would work then. So we have our computer program kind of humming along, doing number crunching stuff on the CPU. All of a sudden, it wants to read in those 50 pieces of information we discussed. And when it needs to read in those 50 pieces of information, it's going to say, oh, I want to read in the first piece of information. Okay, get out of line. Go and read it in. Get back in line. I want to read in the second piece of information. Okay, get out of line. Read it in. Get back in line. So on and so forth. So you can start seeing how that's pretty inefficient, right?
Yeah.
All right. And even worse, we have this thing in here called context switching.
Yeah.
All right. Context switching. That's our act of getting in and out of line. When we get out of line, we have to pack our bag so that we remember where we left off the next time we come back to the CPU. And that way, when we get in line, we also context switch onto the CPU where we unpack our bags to pick up where we left off last time. We don't want our program to start over every single time it gets in the CPU. If you've already ordered your fries and then you have to get back in line, you want to be able to start with your Big Mac on the next pass. All right, so context switching also is happening when you get in and get out of line, and that's also expensive. So we have a whole bunch of stuff in here that, while from a human perspective happens very quickly. Okay, this is kind of the difference between human time and computing time. Okay, so from a human's perspective, this stuff all happens very quickly, but it all adds up to major delays in our computing. Okay, and this is where files fail. Okay, so files are going to be very low performance. That doesn't mean don't use them. Okay, it means use them sparingly and use them under the correct circumstances. So based on this, and I've only given you kind of a cursory level of how computing actually works, but it's high enough for this discussion. When would you maybe say that a file is okay to use based on this discussion?
For for non-speed essential things, like for example, maybe a Word
Yeah, keep going. You're good. Yeah, think about how you're using files in real life now.
Yeah, like a Word file or
So why is that okay? Why is it okay to when you're done writing your paper or whatever and you hit save, why is it okay for that to save to a file, and then the next time you open up Word it loads from a file, when we've gone through this whole thing and said files are slow? Why is that okay?
Because it doesn't really matter if it's slow.
Okay, why not?
Because it won't really make a difference if it's faster.
So from a user's perspective, would you say that when you first double click on Microsoft Word and then you open file xyz.doc, that you're relatively okay waiting 3 or 4 seconds for that file to open? That's not a huge deal to you, right?
Yeah.
Okay, so when we think about the nature of how human beings use computers, we're okay with waiting up front as long as it's fast after that. What we don't like is a whole bunch of little delays, right? You would hate it if you were in the middle of typing something, and every 5 seconds it was like pausing on you, and you didn't know if you didn't hit the keys or something like that. That destroys humanity. Okay, we don't handle that well. So we want it to be fast while we're using it, but we're okay waiting a little bit at the beginning, because what would the trade-off be if we didn't store our Word document in a file? Because we've mentioned here that files are very slow. Well, we can also mention that files are easy and convenient. All right, so it's a trade-off. They're really easy to work with. They're convenient. They don't require any extra work on the user's part in order to use them. They just happen to be slow. If we used a traditional database, which we're kind of moving towards here in the discussion, if we use that, then what we'd have to do is we'd have to get our database up and running so that it was serving our Word documents, and then we have Microsoft Word. It has to somehow be connected to that database so we can actually open the file from there, open the contents of our Word document from the database. There would be a lot of moving parts to gain performance, ultimate performance, that we're not really interested in, right?
Yeah.
Okay, so
yeah.
That's why a file is okay in that situation. So now if we kind of go on the flip side, when is a file not okay? Well, it would be any other time other than that, but where it really gets bogged down is when you have multiple users using an application. All right, so that's kind of an important distinction in today's computing. Historical applications used files all the time because, especially when you loaded stuff initially, or whenever you save something, if you hit save in Microsoft Word and it takes a second for it to save, Again, a human being is okay with that because they performed an action, they expect it to save, they want it to save accurately. If it takes a second to save it, fine. You know, that's not interrupting our workflow, so that's acceptable for us.
Yeah.
But if you had 50 users all using that application, and every single time one of those users saved, you're in the middle of typing your program, typing your file, your Word document, let's say, and one of those other 50 users saves, and your application pauses for a second, that's not acceptable. All right, that's where so that's where more than one user starts bogging down the idea of a file. All right, and most modern applications are multi-user applications, or at the very least, they're multi-threaded applications. And let's just quickly, I don't want to get too deep into threads so that we can spend some of our time in Angular today, but this is important background information for kind of where we're going, because we want to understand how we write our software so that it runs smoothly in the web browser for us. But you know, we need to understand the nature of what's happening under the hood so that we write stuff that doesn't run sluggishly. Have you heard of a thread before?
I have.
Okay. Well,
I don't know exactly what it is, but I've heard of.
Okay, so
single.
it's in your vocabulary somewhere. It's one of those buzzwords. Not necessarily sure what it means. Okay. So a thread is, we're going to compress the history of this down. We're going to say the modern day process. All right, so now what the heck is a process? So again, let's draw a picture. They say a picture is worth 1,000 words. So here's our CPU again. And running on this CPU, we have, let's just call this, we'll call this P, make him a different color. P is a process. These are all processes. Okay, so those guys that are waiting in line for our CPU are actually processes. So we can think of a process as kind of like a program. All right, so they're the guys that actually are getting served by the CPU. So this is the cashier at McDonald's. These are the people who are waiting to order their lunch. All right, these are three different programs, three different processes that are running on the computer at the same time in this example. Now, this process, this might be Microsoft Word, this might be iTunes, this might be Instant Messenger. All right, so from a user's perspective, so you and I are sitting at the computer, we expect all three of these guys to feel like they're all running at the same time, right? That's a human being's expectation of how a computer works. Even though, again, we're using our example of a single core CPU, even though these three guys are actually only getting, let's say first come, first serve service at the CPU. Okay? So, actually only one thing is happening at a time, even though as a human being, we're expecting everything to happen at the same time. The idea here is that CPUs are really, 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 really fast. So as long as it serves these three guys quick enough, we won't know the difference. Even though they're not happening technically at the same time, it'll feel like it's real time to us. All right, that's the idea there. So a process is the means by which it's kind of a container that allows a single application to run independently of other applications on our computer. Well, sometimes an individual process has multiple things that happen at once within it. An example would be Microsoft Word. So when you're, historically, this is way before your time, but you might be working on a Word document and you forgot to save and the power goes out. Well, you've lost everything since the last time you saved. That doesn't really happen anymore because now the Microsoft Word has built-in autosave features where every however often, I don't know, it's probably every 15 seconds or something like that, it's saving your work for you. Not necessarily in your same file because you're in control of the file, but it's saving it in a secondary kind of oh crap file in case something zigs when it's supposed to zag. Well, again, from the user's perspective, you don't want to feel like you're every 15 seconds Microsoft Word is pausing on you while it's saving. You want to feel like those things are all happening simultaneously. So that's where threads come in. So we're going to call this T. We'll make him that color. We'll shrink him down. All right, so this might be Microsoft Word right here. And Microsoft Word's going to have two threads. One thread, for example, is doing the auto-saving stuff. And then the other thread is paying attention to the user's typing and making it show up on the screen. All right, that might be a simple example. There's probably more than two threads in Microsoft Word. But as an example, threads are how we can have more than one thing happen within a single application. Okay?
Yeah.
Historically, before we had threads, what Microsoft Word would have had to do is it would have had to split itself into two separate processes. One process was in charge of the auto-saving, and the other process was in charge of paying attention to the user. And we're going to say that these guys are heavy. All right, so this is a lot of system resources to do something that isn't as much as a full application usually would need to do. So this would have been relatively inefficient. That doesn't mean it didn't work, but it would have been relatively inefficient. In fact, in some ways, it had advantages. So if we take an application like Photoshop, where it's a fairly high-performance application, we want it to be fast. Photoshop might choose to split themselves into multiple processes instead of using multiple threads, for performance reasons, because if I'm arguing that a process is basically a person in line at McDonald's, and let's say you come in and you're ordering lunch for the office, and you bring two other people with you to order lunch for the office. So here is your lunch ordering team. They're all placing one big order, but it's split across three people. You're getting 3 times the CPU time that you would be getting otherwise because you're all processes. That make sense?
Yeah.
Yeah, each process gets CPU time directly. So having multiple processes associated with a single application gives you more actual CPU time. It's not really fair to the other processes on the computer. But if you're dealing with a high performance application like Photoshop, if you're the consumer, if you're the user of Photoshop, you want it to feel fast and you don't care if other programs on the computer are being treated unfairly. You're okay with that. So this is where a modern day application might choose to use multiple processes instead of multiple threads. Because if Photoshop did the multiple thread thing, you would be stuck with this, and these threads are sharing the CPU time that this process gets. Okay?
Yeah, and that's lower than.
Yeah, again, not a big deal. From a human being's perspective, we don't necessarily see it, but from a programmer's perspective, we need to be aware of this, because when we spawn off threads or we do something that's going to create another thread, that's going to impact the amount of CPU time our program is getting, or at least how our program has to divvy up its CPU time. All right, we only get so much time at the register at McDonald's, and if we have multiple things we need to accomplish, we're going to be dividing up that time that we get at the register across all the things we're trying to accomplish. So as a programmer, we need to be aware of this stuff. Make sense?
Yeah.
All right, so this is it goes into way more detail under the hood than this, what's the nature of threads, but we don't need to understand that at this point. We just need to know kind of who's on stage and who's playing as it relates to our programs. Okay, so let's see here. So that's a file. So let's quickly cover the rest of our database history stuff, and then we'll jump back into some Angular code. All right, so when files weren't good enough, what we and one of the weaknesses of files we would have said is even so, regardless of whether or not they were the right tool for the job from a performance perspective, they don't give us anything special in order to actually ask for information from our data. They don't allow us to say, give me the first and last name of the user with user ID XYZ. You know, they don't give us the ability to express that request. That's kind of coming back to what SQL was for. All right, so so if we just kind of go down the list of database history stuff, we had something called a flat file database. So when we first started calling them databases, what that really implied is there is some way of asking that question that I just mentioned. You know, for example, give me the first and last name of some dude who has this user ID. So when we started calling them databases, that implied that there was a mechanism for doing that, for asking that question. Flat file databases had that mechanism, but they were still built on top of the concept of a file. All right? So then, when flat file databases fell out of vogue, when they were no longer cool anymore, we moved to something called a relational database. And there was some stuff in the middle there that I'm purposely skipping, but this hits our high points.
Yeah.
All right, so relational databases, and this is actually another interesting point. So relational databases have been around for a very long time, but what's interesting is you're going to recognize some of these. MySQL is a relational database. Oracle is a relational database. I kind of just showed my hand a little bit here, but one of the questions I often ask is, so you've heard of the company Oracle?
Yeah.
Okay.
Yeah.
Yeah, I usually ask people, what does Oracle make? And pretty often, students don't know what Oracle actually does. They just know they're a tech company. Did you know what Oracle did before I talked about it here?
No. Well,
Yeah, they make a database. So Oracle is kind of our enterprise, super fast database. So, and that comes with a lot of dollar signs after it. So places like Amazon and eBay, they would use Oracle as their relational database because it's very, very high performance. It's for enterprises. Microsoft, SQL. All right, so we can keep going on here. IBM DB2. So a lot of the databases we're aware of today are all relational databases, and relational databases have been around for a very, very, very long time. Now, what's interesting with that is with a relational database, it has a very old goal. And we're just starting to move past them now. In fact, let me just kind of jump ahead. So now we have this idea of cloud storage. Okay, and that kind of falls into the category of cloud computing. Let me start another slide there. And cloud computing is going to be pretty important to us because this is where we're actually going to store our stuff from our applications. We're going to be using a tool in here called Firebase. All right, we'll talk about that. What was that?
I've heard of Firebase.
Okay. Yeah, I used to use a tool called Parse, but
I did too for my iOS apps, and then they shut down. I just moved to Heroku. It's just kind of complicated.
Yep. Okay, yeah, we're on the same page here. So you've done some stuff. Right. You've done some stuff that he hasn't. Then, so that's good. So same thing. I used to use Parse almost exclusively. With my iOS and Android applications, and then the bigger ones I did port over. But any new application I'm starting, I'm using Firebase. And just a week ago, Google bought Firebase about a year and a half ago, but they really didn't. They didn't change the nature of Firebase in that period of time. But about a week ago, to my headache, Google announced this. They basically finally moved Firebase over to their platform. And they added, let's call it 5,000 features to Firebase that makes it really compete with Amazon Web Services. So I mean, Firebase is like, let's call it super legit at this point. But it changed several things in some of my old applications that I had to go back and fix. But it's really good. It's really good now. So, and I think it's here to stay. But in any case, so when we talk about cloud computing, I won't spend a whole lot of time on this, but just for the sake of the video, what we're really talking about is using computing resources on a different computer. All right, that's what we're talking about. And usually that different computer is somebody like Amazon or Google or something like Parse or Firebase, somebody else who has a really, really, really fast computer that isn't also running Microsoft Word and stuff like that, and also is accessible to the rest of the world. Okay, so it's not just on anybody's different computer. It's usually on somebody who has a really fast computer. All right, and computing resources might fall into CPU number crunching, data storage, and data storage usually comes in several different formats. If we're gonna just list quickly maybe there are two, we have queryable data, and they're usually called storage buckets. Okay, storage bucket data. So when we need to store something, where we need to ask, give me the first name and the last name of the person with this user ID, we'd want to store that in their data storage option that is queryable. When we just need to store a big picture that we're going to come back and get later on, we don't care about being able to query it. We'll remember the name of that picture someplace else. We just want the storage bucket, and usually this guy is cheap for lots of storage. So, and this is actually a real problem in computing. So since you've done some iOS stuff, the nature of applications changes a little bit when you are doing mobile applications versus web, but I guess not tons. But especially if you're doing an application that has to store lots of images, storing images using something like Parse is really, really expensive. So if you were to store all your pictures in Parse had a 10 megabyte limit per picture, which is fine, you would start incurring lots of actual charges. You would start getting into their paid tier of storage very quickly, and it would cost you a lot of money. Whereas you can store, let's just use an example, 3 terabytes of data on Amazon S3, for example, which is their storage bucket. 3 terabytes of data is something like $10 a month. So it's not overly expensive. You still have to write the software. You have to write the software in order to interface with it. You have to remember the names of your files, so you can store the names of those 3 terabytes of files inside of Parse, and those are just text strings that aren't going to take up any space. So those would be free. You can store that in Parse for free, and then pay your $10 a month to Amazon to store your actual data, and that's a lot better use of that. All right. So this is kind of so let's just call this our real breakdown of cloud computing. Today, if you go to Amazon Web Services, or now you go to Firebase, there's 50 different things. Kind of the new popular thing that everybody's talking about is data mining and AI. So all of these platforms now, you've maybe seen some of the commercials for IBM Watson. They all have artificial intelligence cloud computing resources now, where you can use it for natural language recognition. You can send it an audio file that has somebody speaking, and it'll send you back text. The voice processing of it, that kind of stuff. So all sorts of different cloud computing type stuff exists. So that's our modern way that we're storing stuff. So we are certainly moving away from relational databases today. But relational databases are still very, very popular. Historically, these were popular because they minimized storage footprint. And on top of that, they were, more recently, they're popular for companies like Amazon or eBay that host their own database server internally. So, you know, these guys have been time tested. They've been around for a long time. The big boys like eBay and Amazon that, you know, they've had applications around for, relatively speaking, a while, well before cloud storage was a thing. So a lot of their applications are already written using SQL to talk to relational databases. So why rewrite the stuff if you already have a security reason to keep your servers on site? So these guys are still very much used today. But historically, the reason that relational databases existed is to minimize the storage footprint. Okay, this was their real motivation for keeping these guys around.
Yeah.
Now, historically, why would we want to minimize storage? You got to think about the years this was happening in. This was in the 1970s and the 1980s, so well before your time.
Yeah.
But, you know, you seem to be familiar with some computer hardware stuff, I'm guessing. You mentioned SSD earlier, so usually if you're throwing out an acronym that quickly, you must be into hardware at least a little bit, right?
Yeah.
Okay, so, you know, let's use this example then. Let's go memory upgrade. So let's say you have a laptop today that has 4 gigabytes of memory in it, and you want to double it to 8 gigabytes of memory. So you're going to go and get another 4 gigabyte chip. How much is a 4 gigabyte chip today?
Probably, let's see.
Just roughly speaking. Maybe about $50?
Probably, yeah,
Yeah,
probably around there.
yeah, let's just say $50. If you order it online, you might be able to get it cheaper, but that's a good enough number. All right. Well, what's a gigabyte? I think, did I cover that stuff?
No, I'm sorry, that was...
I don't remember if I covered that in here. I'm just checking real quick. Yeah, it doesn't look like it, so let's just cover that real quick. So when we talk about actual...
Sorry, you just glitched out. What did you say?
When you talk about data storage, we think about things in terms of megabytes or gigabytes or kilobytes, right?
$17, 4 gigabytes.
Oh, $17.
Yes.
Okay, even cheaper. Fine, $17. All right, so let's go to data storage here real quick. I'm going to create 2 columns.
Yep.
All right, so on one side we have 1 bit. We have we have bits and bytes. That's the 2 sides over here. So 1 byte is equal to 8 bits. Okay, 1 bit is a single 0 or 1. 0 or 1. 1 kilobit is 1,024 bits. 1 megabit is 1,024 kilobits. 1 gigabit is 1,024 megabits. And we'll say 1 terabit, nobody really uses that yet, is 1,024 gigabits. And this is actually, let me do the other one, and I'll tell you a funny, an interesting consumer ploy they use today. So then we have bytes. So we have 1 kilobyte, big B, is 1,024 bytes. 1 megabyte, big B, is 1,024 kilobytes. 1 gigabyte, big B, is 1,024 megabytes. 1 terabyte, big B, is 1,024 gigabytes. So, important thing here is that big B means something different than little b. Okay? So, where this becomes interesting is with internet speeds. When a company, they take advantage of consumers, I feel. So, when a company is selling you internet speeds, and they're selling you a 50 megabit per second internet speed, most people who don't know the difference consider that megabytes. They think they can download at 50 megabytes per second. when actually 50 megabits,
Yeah.
you have to divide that by 8. That's only 6.25 megabytes per second. Okay? It's still fast. That's still plenty fast, but internet speeds are measured in the megabits per second over on this side. Okay?
Yeah.
All right, so kind of an interesting thing there. But so we just talked about 4 gigabytes of data, which would be 4,096 megabytes, is $17. All right, so let's go back to, in 1996, I had a computer, and it had 8 megabytes of memory. Megabytes. And I upgraded it to another 8 megabytes. So I upgraded to 16 megabytes of memory. How much do you think an 8 megabyte memory upgrade was in 1996?
Probably very expensive.
Okay, so first of all, what's a megabyte? So if we take, so 4,096 megabytes is our 4 gigabytes, divided by 8, so that's 512. This guy right here is 512 times more memory than this. Okay? So if you were just guessing, just throw it out there, take 5 seconds to come up with it, what would you guess I spent for 8 megabytes of memory in 1996?
$75.
$1,000.
Holy shit.
$1,000. So, and you have to consider, that's $1,996. So with inflation, that's probably more like $1,500 today. Okay, so what's the purpose of telling you this? It's memory was really expensive. All right, and here's the real kicker. This guy right here, this $1,000 for 8 megabytes of memory, that is after memory started coming down in price. It used to be even more than this, substantially more than this. Okay, so memory used to be really, really, really prohibitively expensive. And not just that, we were also limited on how much memory we could have. So not only was it super expensive, even if you had unlimited dollars, you still were limited on how much memory you could put onto a single chip. All right, 4 gigabytes was unheard of in 1996. In 1996, my hard drive size was 420 megabytes. All right, that was the size of my hard drive, not my system RAM. All right, so with all of this being said, memory was really, really, really expensive, which now you can probably connect the dots and say that's why it was so important for relational databases to minimize that storage footprint. You know, these guys lent themselves to not duplicating any data. Keep your storage footprint down to the absolute minimum, because really every little bit that you store costs real dollars back then. You know, where today we don't care, right? You know, it's like, oh, well, so I could, you know, in a strongly typed language, so, you know, you've done some stuff with iOS. Did you use Objective-C or did you use Swift?
I use Swift.
Okay. So Swift is a little bit weird because it's a strongly typed language, but it acts like a loosely typed language. So you don't really define how you're going to store an integer, but let's just assume that this is the case. Under the hood, I promise you it is. If you only needed to store a number between 1 and 10, for example, you would not store that in a 32-bit integer. You would store that in an 8-bit integer. 8-bit integers can store numbers between negative 128 and positive 127. That's a plenty big range to store your numbers between 0 and 10. Okay? Whereas a 32-bit number can store numbers between negative 2 billion and positive 2 billion. Okay, much bigger container, way too big for you to store the number between 0 and 10. So it's kind of like if you were mailing a golf ball to somebody. You know, you're going to send a golf ball for UPS. through UPS to somebody, but instead of putting it in a nice small little box capable of holding a golf ball, you took like a box that a freezer or a refrigerator used to be in. You threw the golf ball in there, you sealed it up, you took it to UPS. They would look at you like you're crazy, right? It's like, man, this thing weighs nothing. It's like, what's in there? Just one golf ball. All right.
Pretty ineffective.
Right. But in the computing world, we do that all the time. Okay. Today in the computing world, we use 32-bit integers to store any number. If we're only going to store a number between 0 and 10, we don't even think about it. It's not even worth our time as programmers to consider using a different size value to store it, because who cares? Who cares? It's an extra 30 bits of data. Not a big deal. It's throwaway money. Why? Well, you already said $17 for 4 gigabytes. Who cares?
Yeah.
Okay. We effectively have unlimited memory for 99% of the stuff we ever do as programmers. Okay. Yeah. Every now and then we'll bump into a problem where we actually need to pay attention to memory. We're working with video data streams or something like that, where it's like, okay, hold on a second. Now we're dealing with things that actually have size to them, and we need to pay attention. But most of the time, who cares? We're not going to waste our time coming up with the perfect size variable to hold some piece of information we're only going to be using for 5 seconds. But that was not the way programmers operated years ago. They used to have to be really, really careful. In fact, you've heard of this might be another trivia question, Y2K bug?
Nope. Never
heard of the Y2K bug. So you weren't alive in 2000?
Nope.
Is Mom still there? Has she heard of the Y2K bug?
Oh yes.
Okay. And what was it? What do you recall the Y2K bug was?
It was a big nothing at the end of it all. But there was a lot of fear as to what would happen when the year 2000 occurred, to how dates were stored in all of the legacy systems.
Yep. So it really came down to dates. And I mean, it wasn't that it was a big nothing at the end. It was all the efforts to fix the old software ended up working. They ended up getting most of the software updated, but the issues, you mentioned legacy systems. So older software that was written in the 1970s, 1980s, even 1990s, early 1990s, they would store dates in two-digit years. Okay, so it wouldn't be the year 2000 would have been indistinguishable from the year 1900, because they were both 00. So that was the real problem. So anything that, all these billing systems and stuff like that, when they went to run invoices, they wouldn't be able to determine what date came before what other date starting in the year 2000. Because it would have looked like, January 1st, 2000 was January 1st, 1900, which was 100 years ago in their billing system. All right, so, and why is that? This was in the year 2000. Well, we saw it right here. Even in 1996, memory was expensive. We didn't have to be as careful here because we did have 8 megabytes of memory. But a very famous person once said, you will never need more than 32 kilobytes of memory. Okay? That's at least pretty...
32 kilobytes of memory for just browsing.
That's at least pretty close to a quote. Do you know who said that?
I have no idea.
Bill Gates.
Really?
You know who Bill Gates is?
Yeah. Okay. Yeah, the founder of Microsoft.
Yep, Microsoft guy. So Bill Gates once said, "You'll never need more than 32 kilobytes of memory." If that's anything over that is overkill. All right, so that kind of shows you the growth of computing. But memory used to be really expensive, as I mentioned before. It was even more expensive years before that. So years before that, $1,000 may have gotten you 4 kilobytes of memory. Okay, and that's in Four.
4 megabytes.
4 kilobytes of memory. Now, I'm sure there was a day when 4 kilobytes of memory was $1,000. You know, maybe it was in maybe that was in 1985, something like that.
That's crazy.
Yeah. So I mean, well, and you also have to consider with inflation to today's dollars, it's even more, right? So you know that's probably $2,000 back then. Okay, so memory was really expensive, but we also had different types of software, right? We didn't have these video games that were, you know, 9 gigabyte installs and 22 gigabyte installs. We had, you know, our video games back then were text-based and they were, you know, they took up 4K or something. You know, there was a whole different world of computing. We couldn't have seen where things were going to go. Okay, but that's really what the Y2K bug had to do with. It was the 2-digit years instead of 4-digit years, which required us to upgrade a whole bunch of software. And the reason why they wrote that software to use 2-digit years instead of 4-digit years was because of was because they assumed that software wasn't going to be used through the year 2000. They said, "Oh, well, this isn't going to be a problem," and they considered it. But you know, this software, I'm sure, is going to be replaced before the year 2000. So let's not worry about it now. Where a lot of these legacy systems are still around today. My wife is a COBOL programmer. She works for Western Illinois University, and she's writing software for systems that have been around for 30 and 40 years. Because they spent so many hours, they have thousands and thousands and thousands of hours in this software that works. So why rewrite it in a new language when it currently works? You know, and she's just adding features to old software. You know, that's, you know, it's a trade-off. A lot of these companies, they don't have the dollars today to rewrite everything, but they have the dollars today to update what they already have. So rather than spending $1 million right now, like pulling a Band-Aid off to get it all upgraded, they're instead going to spend $100,000 a year to keep it going. Yeah. So that's kind of the world we live in. All right, so let me just take another minute here and let me kind of tell you what the plan is moving forward. So I've been talking to the moms. And so what I'm going to do is I'm going to come up with a couple of software applications, a project for you guys to work on over the summer. And then when we meet, we're going to be talking about the kind of the features you'll need to take your, you know, go to the next step in your project.
Yeah.
All right. So I'm going to send you an email before the end of the weekend with with kind of the projects. Now, my guess is, well, you tell me your opinion on this. Should I have come up with 2 different projects, or do you want to have one project that each of you work on independently that you can then collaborate if one of you is running into some issues on on a feature or something like that? Does that maybe make more sense?
Yeah, I think so.
Okay, so I'll do that. Let me come up with one project, and we'll do it in Angular. It sounds like you were interested in mobile stuff, iOS stuff, and things.
I'm also interested in learning web. I think it's where mobile devices really want native applications, but laptops and PCs really want web applications. So I think it's important to know that.
Gotcha. So yeah, I can completely agree. Except for the fact that native mobile applications are way more fun to write than web.
Yes.
It's not even close. All right. So let's see. So in the meantime, let's just go ahead and let's finish. Go ahead and read through the rest of these things just so you have these under your belt. So the Angular DOM is not that important, but Angular events, this is helpful. So I would say Angular events, Angular forms, pretty helpful. Okay. Validation as well. But go ahead and just read through the rest of these. So we have those under our belt in terms of just knowledge base. I'll send you a project before the end of the weekend, and then what I'll do is I'll probably give you kind of like a first assignment for next week for you to think about stage 1 of that project and maybe just get the very first parts of it done. That sound fair?
That's good.
Okay, perfect. So, and I think are we on for next week? I know there's some dates that we're not meeting, and there's some dates when you're gone and he's not, and vice versa. But I think we're on for next week with somebody.
Yeah, we are on.
Okay, and I'm gonna upload this video to YouTube, and then I'll send both of you guys the link to it, so you'll have it, and so you could refer back to it or whatever. All right. So I will see you same time, same station next week.
All right.
All right. You have a good one.
Bye.
Bye-bye.
You too.